Today we're very happy to have Catherine Rychert as our speaker to kick off the 2025 webinar series. So Catherine, also known as Kate, took her BA from Boston University in 2001 and her PhD from Brown University in 2007. She then carried out postdoc research at the Scripps Institution of Oceanography from 2007 to 2009. Kate was a fellow of the UK Natural and Environmental Research Council at the University of Bristol before joining the University of Hampton as a faculty in 2013. During her time in the UK, she received the Bulwell Award from the British Geophysical Association and the Fowler Prize from the Royal Astronomical Society. And since 2021, Kate returned to the US and joined Woods-Hole Oceanographic Institution as an associate scientist with tenure. Kate is an expert in exploring the Earth's lithosphere and asthenosphere, with her research spanning active plate boundaries to stable continental cratons. She employs a variety of seismological methods to investigate the structure, composition, deformation, and the melting processes within these layers of the Earth. And her recent project, this PyLab experiment, had yielded significant insights into the lithosphere and asthenosphere boundary in the settings of mid-ocean ridge and oceanic transform fault. So today, Kate will share with us the results of the PyLab experiment and provide a discussion from a global perspective. So Kate, please take it away.
Great. Thanks very much for that very nice introduction, Jianhua. Yes, so today I'll talk about a dynamic lithosphere-asthenosphere boundary dictated by variations in melt generation and migration. I'm going to talk about the PyLab experiment at the Mid-Atlantic Ridge and then put that into a global perspective. And I'd really like to first thank the students, in particular the students, everybody, but the students and postdocs who contributed to this work. And those include Saikiran Theramina, Xinguo Wang, Petros Bogiatsis, Matthew Agias, David Slaphorst, Kostas Leprokoropoulos, Utpal Saikia, and Yuhang Dai. Okay, so the notion of a rigid lithospheric plate that transitions to a weaker asthenosphere is a central aspect of plate tectonic theory. And typically, we describe this transition thermally. In other words, lithosphere heat transfers by conduction, and in the asthenosphere, it's transferred by advection, and the 1D predicted temperature profiles for these two different forms of heat transfer intersect at some point, and that's typically where we describe the lithosphere-asthenosphere boundary. This boundary is highly debated, and so before I go on and to start to describe that, I just want to tell you why it is important. It has broad implications for our understanding of mantle dynamics, given that it's so central to plate tectonic theory. It's important to our understanding of the evolution and origin of the continents. And it has broad implications for our understanding of things like the driving forces of plate tectonics. It even has implications for natural disasters, given that they come from these plate tectonic processes. These include volcanoes, earthquakes, and tsunamis. And it even has implications for things as broad as climate science and Earth's habitability. So there are many, many observations that are consistent with the thermal model. And here I'll talk about the oceanic lithosphere, because it's probably the ideal place to consider the lithosphere-asthenosphere boundary, given that if it is defined thermally, we have well-predicted models for how it should age with depth and has a relatively simple and short history. The lithosphere should get colder and thicker as it ages and moves away from the ridge. And we can observe this by looking at shear wave velocities from seismic tomography. These show us that velocities get faster and also extend to deeper depth beneath older aged lithosphere. This is true in age averaged bins. And that's what we expect for given the the temperature velocity relationships. And so that's great. It means that overall, temperature plays an important role in dictating the LAB. We also observe that there's a gradual velocity gradient in depth, and that is what we predict for a thermal model, given the profiles I just showed you. And this is also predicted by experimental constraints that show, that they predict a gradual decrease in velocity with depth for a young and also older lithosphere, and that this should get colder and also more broad as we go to older ages. We also have a host of observations from scattered waves. These are phases that have converted or reflected at a given seismic discontinuity. And on the top, I show in the symbols observations from normal lithosphere that has not been affected by hotspots. And what you can see is they're really picking out a pretty good relationship or increase in depth with age. And this agrees pretty well with the predicted decrease in viscosity from geodynamic models shown by the contours in the background. It's also very similar to the solid eye depths shown by the cyan and the pink lines for the 125 ppm and 500 ppm water contents. There is more scatter when we consider all oceanic lithosphere, like considering those also affected by hotspots shown by the more redder symbols here. And that suggests that there's more variability potentially related to hotspots. But we can also see that still the majority of symbols are also in agreement with the thickening with age from the isotherms shown in the background for predictions from the plate model in black and half-space cooling model with the dashed gray. So overall, temperature is still playing a major role in dictating lithospheric thickness. There's a little bit more scatter than you might predict, and a lot more scatter if you consider hotspots. So perhaps some greater complexity. In addition, all of these observations, despite that they're near where we predict the LAB depth to be, require something sharper than the much more gradual prediction for a purely thermal model, something more like the dashed black line here in comparison to these much more gradual gradients in depth. And that also suggests some degree of greater complexity. Not just scattered waves. There are also other observations, a host of them, that cannot be explained by temperature alone. For instance, observations of very slow seismic velocities and observations of very high conductivities. I'm showing you here 2 examples from the East Pacific Rise, but there are many others. So because of these very different takes on what exactly defines the LAB and how it can be described, there's some controversy. And therefore, it's been proposed that each methodology has its own LAB. And this is disturbing because what that implies is that the different sensitivities and resolutions are telling us something different in every case, and that it's not necessarily the rheologic LAB, which is the really important thing. That's exactly what we want to know, right? So that's a problem. And so therefore, it's also been proposed that there are a variety of sub-Solidus possibilities that can explain, in particular, scattered wave observations, which I described before. And these would not necessarily affect the mantle rheology and therefore would not be the rheological LAB. These include things like a change in anisotropy with depth, the oxidation state of the mantle, elastically accommodated grain boundary sliding. So in other words, an increased effect of H2O on seismic waves in comparison to typical expectations. And also the possibility that near Solidus conditions have a greater effect on seismic waves than typically anticipated. I won't go into the detail, but because these have each been proposed to describe an individual or a group of observations or, from a single methodology or certain methodologies or a single location, Each one of them has difficulty describing all of the observations from all the different ranges of sensitivities and resolutions in all the different locations. Perhaps a more simple explanation is a small amount of partial melt. Partial melt is interesting because if it exists in the quantities that are required to explain some of the observations, it's predicted to decrease the viscosity of the mantle. And in that case, it would affect mantle dynamics, and we'd really like to know a lot more about where that melt is and how much melt there is, what form it's in. However, melt has been proposed to exist in a variety of ways. These include, for instance, from active source imaging, these thin melt channels at the base of the plate, also from geodynamic modeling, that would be along the base of the plate here. Melt has also been proposed to exist in these very wide melt triangle areas, or this entire area here from surface wave imaging, or in very, very narrow melt column beneath the ridge. This is from MT. You can see this narrow melt column here. It's also been proposed to exist in very complicated melt channels from geodynamic modeling and very thin layered melts from receiver functions. We'd also like to know how it drops off in depth. These are the transect studies from Garrity and Helmberger showing that there may be a very gradual drop off in melt with depth, or it could be quite abrupt, as suggested by these receiver function imaging results here, and also from the active source images. So we'd like to know a lot more about this. But as I said, many studies use a single methodology in a single location with single set of resolution and sensitivity. And our idea was to go to a single location and use a range of methodologies with a range of resolutions and sensitivities, and also to study a different kind of spreading center. Typically, most studies are at the East Pacific Rise, which makes sense. The Pacific is a very big ocean and very interesting, but we wanted to go to a place that had slower spreading, like the Mid-Atlantic Ridge, since it's predicted to have much different behavior. And so this is a PyLab experiment. It was deployed from 2016 to 2017, 1 year, and it consisted of 39 ocean bottom seismic instruments and 39 ocean bottom magnetotelluric instruments. They were co-located, shown by the white symbols here, and they were in 3 lines, 2 main lines and a more northern line, and centered on the chain fracture zone, as you can see here. They crossed 2 ridge segments, one here and also one here in the south. And we also collected a host of other marine geophysical data, including gravity, magnetics, and swath. And there was also an active source component. There were also several other experiments, including transatlantic iLab, CALab, from Steve Constable, Eurolab, and the transatlantic iLab was from Satish Song and Ingo Grabmeier. All right, so I'm going to start off with surface waves. Surface waves are waves that travel across the surface of the Earth. I'm just showing, and they give you a good idea of the absolute velocities. And I'm just showing you that we have good ray coverage for teleseismic and ambient noise tomography. And I'm going to jump right into the results and show you that at shallow depths, here 26 kilometers, we have slow velocities beneath the ridge axis, and we have faster velocities at older ages. And that's great. That's what we expect for a cooling plate. You can also see this in cross-section. Here I'm showing you the northern line, where beneath the ridge, which is right here, we have slower velocities, and we have faster velocities at older ages. And that's true in the south as well. Slower velocities beneath the ridge, and faster velocities at older ages.
Hey, this is Jessica Warren. Sorry to interrupt, but I'm not seeing your slides anymore.
Oh.
I don't know if it's just me.
What should I do?
I think I can see your slides. Can other
Okay,
people
maybe I'm gonna
respond?
leave. Sorry to interrupt. I'm gonna leave and come back in.
Okay.
Okay.
Okay. Okay. Okay, hopefully that works out. I'm happy to start and restart as you like. But when you go to deeper depths, here I'm showing 78 kilometers depth, you can see that we have punctuated anomalies. They are not necessarily beneath the ridge axis, and in some cases, they are several hundred kilometers off axis. That's much different than the typical paradigm. And we can also see that in the cross sections. You can see here these very large off-axis anomalies that are punctuated. We also see, interestingly, evidence for a lithospheric drip right here. Okay, I'm going to move on to receiver functions before coming back to that model. First, I'm going to show you some S to P receiver functions, or S waves that convert to P waves at a discontinuity. And then I'll show you some P to S receiver functions, P waves that convert to S waves at a discontinuity. And when we deconvolve one from the other, we get these impulse response, or an image of Earth's discontinuity structure. So starting with the STP receiver functions, we find a MOHO in all the waveforms across the array, which is pretty cool and pretty rare. And it varies from about 4 kilometers in some cases to 8 kilometers in the deepest regions. This is quite interesting. It's more variable than the Pacific, for instance. And if you squint your eyes, you might see that the shallowest MOHO depths also correspond to the regions of the higher mantle Bouguer gravity anomalies, whereas the thicker MOHOs correspond to the regions of the lower residual mantle Bouguer anomalies from gravity. And that's what you expect: thinner crust, higher RMBA. So that means that the MOHO is dominating that signal, and good agreement. Okay, moving to deeper depths. Here I'm showing you S to P receiver function resulting cross-section now. We see the MOHO across this entire cross-section. I'm showing you this cross-section in the south. The ridge axis is right here. And we find a beautiful LAB phase at about 30 kilometers depth beneath the ridge. It migrates to deeper depths as we move to older lithosphere, around 70 to 80 kilometers depth beneath the oldest 30 million year old lithosphere. That's a beautiful result. That's all we wanted to get. You can see it in cross section as well. We were like happy to just go home at that point. But in fact, it's not as simple everywhere, and that's good because it gives us something to talk about. Okay, so on the eastern side of this cross section, you can see that there's just a blip. We do not image this beautiful LAB. But the blip does occur, I'll point out, just above the slowest anomaly from the shear wave velocities of surface waves. So that's promising and suggests that there might be something else that's more complicated going on. And we'll talk more about that. But before I go on, I want to point out that there was also a recent study from Active Source that showed there's a discontinuity exactly in agreement with this beautiful simple phase that we saw in the West. And this suggests that this phase is actually very sharp, occurring over 1 kilometer or less. So that's an extremely sharp LAB and super interesting, and really a good justification for doing more joint active source, passive source experiments in the future. Okay, so going on to those complications. Here I have the simple story on the right-hand side in the south. In the north, we found much more complications with strange undulations. You might expect that if you look at the surface wave shear velocities, given that they are kind of very, very punctuated and not very simple. So let's talk more about that in a minute. We'll go back to the resolution. First, I want to just give you a reason that we think it might be relatively simple on the west in comparison to the east. Here I'm showing you P to S receiver functions, imaging of the mantle transition zone much deeper at 400 to 600 kilometers depth. You can see here the depths of the 410 and the 660 on the left. When we differentiate these, we get the thickness of the transition zone. We find about 20 kilometers of thinning on the western side of our study area. That's interesting and completely unexpected. Now, typically, we think of transition zone thinning occurring in locations of hotspot upwellings and thickening occurring in locations of subduction zones. We don't typically assume that the ridge flow has a large relationship with the deeper mantle. However, when we compared the velocities from global velocity models, many of them, beneath the ridge, to velocities beneath the in the transition zone depths beneath the rest of the ocean basins, we found that particularly beneath the mid-Atlantic ridge, there was a clear, significant difference in that the velocities were much slower in all of the velocity models in comparison to those beneath the older ages. So that supports our hypothesis that there is slow, deep upwelling beneath the mid-Atlantic ridge. It's quite interesting. And it could explain also why we have the much more simple story of the LAB in the West, in that if it's supplied by some deep upwelling, that constant upwelling and potentially decompression melting is allowing us to see that beautiful LAB along the permeability boundary, whereas melt might be more sporadic or a different character in other locations. The reason it's probably upwelling in the West as well, and not just directly beneath the ridges, is because we have this long offset transform here, and the upwelling is probably just cutting across from these ridge segments in the south to the ridge segment that's over here in the east. Okay, bringing in the magnetotellurics. In the background, I am plotting the resistivity anomalies, and I have shear wave velocities from surface waves contoured in black. The receiver function result is shown in purple, where it's significant from 0. And what we see is that overall, there's pretty good agreement. Both, conductivity and surface wave shear velocities show evidence for punctuated anomalies. They both show evidence for a drip. There's also evidence for kind of a very simple velocity drop with depth, simple drop in resistivity with depth, in the location where we were able to image with receiver functions, and that makes sense. What's new here and exciting is that we saw evidence for this high conductivity channel beneath the eastern side of the southern transect. That's brand new, and surface waves only resolved this kind of blip. That's not unexpected, given that surface wave models are generally parameterized in a much smoother, broader sense. Talking about why we might not resolve thin channels with receiver functions, as I showed you here, like the receiver functions just resolve this tiny blip here. If you think about it, receiver functions have, in the instance of a channel, have a phase that's converted at both the base and the top of the channel, and their opposite polarities. As that channel gets thinner, the phases begin to destructively interfere, and you start to lose amplitude. That's just what I'm showing you here. And when you get to about 10 kilometers, it makes it very difficult to see the anomaly. Whereas our resolution testing with conductivity shows that we are able to resolve relatively thin channels. And also things like punctuated anomalies. However, it's been shown many times that STP receiver functions cannot image very sharp topography and are really only the best at imaging relatively flat structures. And so that's probably why we image the LAB in only certain locations where it's relatively simple and not channelized. Okay, so overall, we have this good agreement. We're really happy about that, but we would like to do a better job at bringing things together. And so that was our next goal. And so this is what we did. Because we know that that surface wave shear velocity models are highly dependent on the starting model and smoothing, and a wide variety of models are acceptable, whereas the resistivity imaging has less dependence on the starting model. We decided to see if we could better fit the surface wave model to the resistivity model. And this is what we did. We made a half-space pooling model with temperature here. And we then translated that half-space model to a shear wave velocity model and a resistivity model using petrophysical predictions. Okay, then we plot those predictions one-to-one, here shear velocities versus log resistivity. And you can see the predictions for a thermal model in black. You have some variability because of the different pressures. And that's great. Then we decided, well, we're going to add some melt because we think there might be some melt there. And that's shown in brown here with greater quantities of hydration as we move from the right to the left. Okay, so that's our prediction theoretically. It is not linear, obviously, but horseshoes and hand grenades, we threw a line through it. That's the gray line. Okay, so then we went back and considered our data. And you can see here that when we plot line 1, this is the northern line, the shear velocities from the data versus the resistivities, there's a histogram in the background, and compare it to that black line, it's really not doing bad. We're kind of clustered around that line. We do the same thing in the south. And you can see, again, it's clustered around that black line. The correlation coefficients are not perfect, but overall, we're doing a pretty good job in terms of being close to the petrological predictions. So we continued onwards. We had to reparameterize the surface wave model because it was done at a very broad scale, and we wanted to incorporate those fine details from the resistivity model. And so you can see the reparameterized surface wave model at a finer resolution in the top model. We then took the MT model and translated it using that linear relationship to a predicted shear wave velocity model. That's shown here. And then we used this predicted shear wave velocity model to re-invert the phase velocities for shear velocities. And this is our outcome. In the south and the north, you can see that the anomalies are really coming out really well. We still find these very beautiful punctuated anomalies. The drip and lithosphere are really showing up beautifully. And what's really interesting to me is that in the south, we see this beautiful channel structure. It may be the first ever surface wave channel LAB. But the thing that's really important to point out here is that this model on the bottom fits the phase velocity data just as well as the original surface wave model I showed you. So that's really important. It means that there is no difference between these, and we are able to fit, we can fit our data with the models that are pretty consistent from both MT and seismic velocities. Okay, so now stepping back, if we plot our new shear velocity model versus resistivity, as the histogram in the background here, you can see that there's a better correlation. And there's also pretty good agreement with the petrophysical predictions, again, for purely thermal model in black. And then increasing amounts of melt as you go from here pink to purple to brown, and then increasing amounts of hydration in the melt as you go from right to left across these dots. So we can use these petrophysical predictions and our observations to then try to pull out where we predict temperature anomalies and also melt and hydration anomalies. And that's what we did. So on the right, I'm showing you the predicted temperature anomalies in the highly anomalous region. This is a northern line, and this is a southern line. You can see the punctuated anomalies and the channel. And then these are the locations where we predict melt. It's up to about 4% melt. And then this is the amount of hydration that we predict in the melt in the middle row. Yeah, so the hydration is pretty high. It's probably at least an order of magnitude higher than rock samples that are typically observed at the mid-ocean ridges. So that's interesting. We were wondering, well, if it's not hydration, then what else is it? We looked into CO2, but then we also found that we still need, again, much higher quantities, about an order of magnitude larger than observed at samples at the mid-Atlantic ridge. So then the other possibility is sulfide melt, but again, it was quite high. And I have all the numbers here, but it just hand shoes and horse grenades, it's like an order of magnitude higher. Okay. So the other so one possibility is that there's some combination of these volatiles. Another possibility is that it's some artifact of resolution. So the MT model is done in 2D, and that can cause artifacts. What's going on now is Shengguo Wang, who did the MT model, is now working on a whole 3D model of the Atlantic. It's just taking some time because it's very computationally intensive, but we will see, because these hydration, the volatile anomalies all come from the MT imaging. So we'll see if we can reduce these at all by doing a higher resolution, a more computationally and also more robust model. The other possibility is that what's down in the mantle is not making it out, or some other factor of error between the observations and the experimental predictions that we are not aware of. Okay, so just now, since we've kind of gone through all of that, I want to say briefly that we did do a good job of bringing things together. And here I'm showing you the surface wave shear velocities in the background, the resistivity values contoured in black, and the receiver function discontinuity structures in purple. And what you can see is they really have come together, and that's great. I mean, we're super excited about that. The fact that this channel was in the same location, the punctuated anomalies, the drip, the receiver function seem to be kind of making sense in terms of where they're robust in more simple areas where there's more simple anomaly structure at depth. So that's great, but we acknowledge that we massaged this. We brought this together intentionally. But what we have now discovered recently is that we have a completely independent constraint that is very consistent with this model. This is work by Petros Bogiatsis that is still in the works. But what we find is that there are shear velocities from body waves shown by the colors in the background that also show punctuated anomalies. And they're in excellent agreement with the locations of the resistivity anomalies. Those are shown by the contours on top of the body wave anomalies. They also have very similar structures in terms of evidence for lithospheric drip, punctuated anomalies in the lithosphere, and high velocity anomalies. And very interestingly and very excitingly, that channel is not an artifact because it shows up extremely clearly in the body wave tomography result. And we're super excited to kind of bring these things together and go for this a little bit more to get a little bit more precise detail. Okay, so that was kind of most of the structural constraints, but we have some other pieces of evidence that can help us really understand what's going on in the region. Here I'm going to show you some anisotropy results. This is the SKS splitting. On the left, I have our result, and I'm comparing it to the SKS splitting from the East Pacific rise from the MELT experiment. So you can see in the MELT experiment, the alignment is showing you, the direction is showing you alignment that's generally in close to this plate spreading direction, or absolute plate motion. They're very close here, and they're pretty consistent, and it goes right across the ridge axis with not a lot of variation. That's what's predicted for strain that's caused by shearing from plate motions, and so that's associated alignment of olivine fast directions. So that's an excellent result. When you compare to our result, which is shown on the left, it's very different. Away from the ridge, we find splitting directions that are close to spreading direction, and also APM, which are very close here. Those are shown in blue. They're more muted in magnitude in comparison to the EPR, which is generally opposite of the sense that's predicted by geodynamic modeling from, for instance, Blackman and Kendall. That's probably because of the complex flow structures that I showed you before, and that may also explain some of these SKS splitting measurements that are kind of not precisely aligned with plate motions. But in general, that's what we find, kind of generally plate motion, just relatively muted. What's really interesting and extremely different is that near the ridge axis, we have very large magnitude splitting. And many of the splits are close to parallel with the ridge axis instead of the plate motions. And these large splits are much greater than you would expect for the alignment of olivine. And that's how we would distinguish them. We're showing things in red that we cannot explain by pure alignment of olivine. And so what can explain these things? It's probably likely that we have some aligned partial melt. And how can this happen in one place and not another? I guess we went back and looked at the seismic velocity structures. So in the East Pacific Rise, you can see that the shear velocity contours are relatively horizontal because the ridge is spreading relatively quickly and things are moving out very fast. And things look more horizontal. And so if you have aligned olivine, it's going to look like this. And if there is aligned melt, you don't really have any way to focus it in any kind of vertical manner. It's probably more aligned in horizontal flat layers, and therefore would not necessarily give you any azimuthal anisotropy. Whereas if we consider the mid-Atlantic ridge, you can see that if we have olivine, sure, you can have some alignment like this, but near the ridge axis, we have these very steep marginal edges near the ridge in the shear velocity model. And these can probably support some degree of horizontal alignment of thin sheets parallel to the ridge axis that would easily be able to explain the observed splitting. And what's interesting is that this may also affect our understanding of the way that the plate tectonics are driven in the two different oceans. You know, the classic model we know in the Pacific from Forsyth is that the subducting slabs and the force of gravity is pulling the plates down, and that is what's driving the system to first order. In the Atlantic, there is no ring of fire such as that surrounds the Pacific. And so exactly why the plates are spreading is not precisely known. However, if we have this buoyancy force beneath the ridge, then we may have ridge push. In other words, buoyancy force pushing the ridge up and pushing the plates out, playing a larger role, at least in the Pacific. And this is also evidenced in the topography of the ridges, given that the mid-Atlantic ridge sits significantly higher than the East Pacific Rise in comparison to the surrounding ocean basin. And the melt may also play an important role in decoupling the lithosphere from the asthenosphere and allowing the plates to flow. Okay, so bringing all of this together now, we have observed a lithosphere that thickens with age, but not always monotonically. There's evidence for a lithospheric drip. We also have evidence for a location where we have a relatively simple age progression and a relatively gradual drop-off in velocity and potentially melt with depth. In the asthenosphere, we have punctuated anomalies that are likely indicating ascent of asthenospheric material and potentially decompression melting. There's also evidence of a thin channel in the southeast and melt accumulated beneath the permeability boundary. And then here, likely melt has a gradual drop off with depth. Another interesting thing is that while different dynamics have been proposed at slower spreading center, for instance, in the classic Richter rule model shown here by geodynamic modeling, the symmetry of these Richter rules is typically perpendicular to the ridge axis. Whereas if we look at our anomalies, we're seeing these things kind of going opposite to that direction, parallel to the ridge axis. And exactly why that is not known. One possibility is that we're at very young ages where these mature Richter rules have yet to develop. Another possibility is that we are at these very long offset transforms where very young lithosphere is juxtaposed against very old lithosphere, and this can cause instabilities, including lithospheric drips and compensating lithospheric upwellings. So more work to be done on that. Okay, so in synthesis for the PyLab experiment, we observe melt and likely hydrated melt in a thin channel. Also in thicker channels or multiple channels with gradual drop off with depth. We also observe it in punctuated anomalies at depth. If melt exists in the quantities that we require to explain our anomalies, it likely decreases the viscosity of the asthenosphere and defines the plate. Therefore, the lithosphere-asthenosphere boundary is likely determined by melt generation and migration. And we've seen this in a variety of different ways, both laterally and likely temporally. And therefore, this may reconcile the various reports of melts in a variety of forms and locations that I described before. So here I'm just showing you a compilation of all the melt forms. Here it's like giant melt triangles from the melt experiment, very thin things from very thin anomalies from MT. And all of these can likely be the case at different times and locations if the LAB is very dynamic. And this is also probably true for subduction zones where there's also been a range of different forms of melt proposed beneath the plate. Thin channels, many channels, and also very, very wide anomalies. And this kind of dynamics are also supported by geodynamic modeling of two-phase flow, which finds porosity waves, in other words, ephemeral melt-rich pockets that form owing to viscous resistance to compaction and decompaction of the solid flow. This is a result from Simidol, where you can see that these porosity waves form. They accumulate over some time, and more melt accumulates. And then at some point, enough melt accumulates and the melt leaves the system altogether. And some melt will actually freeze into the lithosphere as well. And these variable dynamics are a likely explanation for what we're seeing. Okay, so just putting this into a global perspective here, our results from the simple southwest line are shown with the blue diamonds here, and those fall into really good agreement with the rest of the global results in terms of the depth of the LAB from scattered waves, which is really great. However, overall, despite the fact that we require melt to explain these results, we know that temperature is a first order role. And we know this from many, many kinds of observations. This is just one where we showed the crustal ages from crust 1.0 and compared them to simple clustering analysis of dispersion curves. And you can see there's great similarity between these. And similarly, we see the very simple changes in average surface wave anomaly, surface wave 1D profiles as you go from youngest to oldest ocean lithosphere and towards the oldest cratonic lithosphere. And I'm not going to go into this in detail, but just say that that's true on average, but the gray areas here show all the variable 1D profiles that go into those averages, and there's much more variability. Okay, so what I really want to talk about before the end is the global compilations. So in this study, we compiled a large interdisciplinary data set of LAB depths. We used heat flow, seismic tomography, receiver functions, magnetotellurics, and petrology. We had to use a large amount of assumptions and decisions to distill these into LAB depths. And you may not like those decisions, and that's totally fine, because the compilations will be available as a resource for the community so that you can make your own sets of assumptions and decisions. Okay. We also collected data from 2 focus sites, in particular because observations, for instance, from petrology are limited to locations where we actually have rocks coming out of the mantle. And in addition, magnetotelluric constraints beneath the continents for the LAB are challenging. And so we were able to just demonstrate that results from xenoliths here, from petrology, and from melts generally pick out predicted geotherms and adiabats, and we can find LAB depths that generally agree beneath the basin and range, which is an example of young continental lithosphere, and the Catfall Craton, an example of old continental lithosphere. There's a first order difference between the LABs of the two, and general agreement overall in terms of these depths. There's a fair amount, so the MT, as I said, has difficulty distinguishing the LAB in terms of the actual 1D profile. But what we did see is that there seemed to be a drop in variability in MT resistivity near the depths of these other LABs. And so that's maybe an indicator if the lithosphere is more heterogeneous than the flowing asthenosphere. Okay, so overall, we had these global compilations that show general agreement, and from heat flow on the left, seismic tomography on the right, scattered waves in the bottom left, and these generally agree with the seafloor ages from crust 1.0. They're thickening with age, so to first order temperature dictates the LAB. And we can also see this in age average bins. There's overall agreement. Here I have shear wave velocities from surface waves in the background. The plate model, 1100 and 1300 degrees in red, half-space cooling, gray dashed, surface waves in black, MT in gray, scattered waves in white, and solidi in cyan and pink. And you can see they're generally picking out an LAB. The petrology is in yellow, diamonds. The depths are showing us that we definitely are shallower than the half-space cooling model, and in many cases shallower than the 1300 degree isotherm from the plate model. And this is a very thin plate model. It's assuming 90 kilometers, which is thinner than the paradigm in the textbooks of like 95 to 100, say. This means, and some are much shallower than that. So it's suggesting that we have a divergence from the plate model at earlier ages in the typical 70-degree paradigm, which is interesting. In addition, there's generally a paradigm in the textbooks that the oldest Archean lithosphere is something like 200, 250 kilometers or more in thickness, whereas our depths, overlap in terms of error bars, but are all substantially shallower than that, around 162 to 177 kilometers depth, which is just different than we typically think. So the other really interesting thing is that the oceans, we're suggesting the plate model or divergence from the plate model at older age, from the half-space cooling model at older ages. This is consistent with observations, obviously, from heat flow and bathymetry, but it's much different than these many surface wave models that have argued for the half-space cooling all the way to the oldest ages. But our model also suggests that there could be greater complexity. And when we look not on average, but at single transects, this is the same transect as actually this model. You can also see that there's sometimes this greater complexity, and whether or not that's a matter of resolution can be debated. But our model, an in situ model, suggests that it could be more reality. Okay, so overall, this is also consistent in this global model that we show with the greater variability with the model that we saw from PyLab. And I also want to take a moment to just mention that the continents are also different than the classic paradigm in that we typically think of this this very deep depths extending over this great area, hundreds of many hundreds of kilometers, but in these models it extends over a very, very small area, 1 or 2 pixels of these models. For instance, in the heat flow model and the surface wave tomography does not extend to 250, but is and only a couple bins are greater than 200. So what we suggest is that these depths may not be reached at all, but could be artifacts of resolution. And I can explain that more. The other possibility is that these depths are reached over very small lateral areas and could be indicative of things like lithospheric drips, which is also just different than we typically think. And so you can see this, again, the difference between the classic paradigm of in age averages, where you have this general monotonic, aging beneath the continents and also beneath the oceans, which is much different than these kind of individual transects, and also the more corrugated look of the continents that you see from geochemical inferences. Okay, so in conclusion, temperature plays a first-order role in dictating LAB depths. Our LAB depths are shallower than typically portrayed in textbooks or in most of the literature. This suggests that there is a higher mental potential temperature and or a solidus definition of the LAB, and other factors besides temperature are important. LAB depths are also more variable, and the LAB is likely more dynamic than typically considered. And I also have some slides that I to just show some of the other work that we've been doing with seismicity, and that I won't go into in detail, but just showing you that we had some really cool results about barriers and asperities and deeper seismicity than expected. Tidal triggering of microseismicity, a really cool observation of an earthquake that was really unique in Romanche. And then also we've been doing some work on doing joint solid Earth oceanographic investigations to incorporate Earth's motions and understanding of seismicity into oceanographic estimates for current flows in the Atlantic and also current slowing that can potentially affect climate change. And doing this in kind of a broader scale with smart cables and in a much broader group is kind of one of our bigger aspirations. And I welcome any questions on that as well. Thank you.
So thanks, Kate, for the wonderful presentation. There are already 2 questions from Zach Ilan in the chat. So Zach, do you want to unmute yourself and ask the question?
Sure. Okay, thanks for a great talk. Sorry, I meant to just ask them as you went along. Yeah, my first question was when you were showing kind of the comparison between the surface wave structure and the resistivity structure, and you said, and look, we see the drip in the resistivity structure. And I guess I was squinting and finding it a little hard to see that. And if you sort of just compare the 2 structures, it's not super obvious to me that many things actually correlate between them, except like structure C is clearly very, very conductive and very slow. But that structure D in the resistivity, it's medium resistive, but there's a ton of stuff that's more resistive at the same depth that actually correlates with low seismic velocities. So just curious if you could sort of comment on that, and then especially how that knocks on to the joint inversion.
Yeah, I mean, I guess resistivity is interesting, right? I mean, it's definitely not showing a high conductivity anomaly here. And the thing is that resistivity is like super sensitive to high conductivity, but not necessarily like how low, you know what I mean? It's kind of like attenuation in seismic imaging, like how low the resistivity, how low the conductivity is, low the resistivity is, you know what I mean? Yeah, so that's my kind of explanation for that. It's there, you can see that it's like not conductive. And then I guess the surface wave model really prefers it. And so I love that when you kind of put them together, you can see like where their, low resistivity is, we see that, really, really high seismic velocity. And that's, I think, pretty convincing to me. And it's also pretty well supported by the body wave tomography, which, also sees like the lack of this, the very high conductivity anomalies.
So yeah, my second question was actually about the body wave tomography, especially this panel E and comparing it to what's on the right. I was just sort of curious how such a thin channel produced sufficiently large travel time anomalies to be seen in what I think you said was teleseismic body wave tomography. Is that correct?
Oh, no.
It's not teleseismic. It's all local.
It's local and teleseismic. Yeah, that's how we got it.
Do you know how deep
the surface, the shallow part of this model is like super well resolved because we had these like local events. Yeah. Mm-hmm.
Oh, and how deep were they?
Oh, you can see in our seismicity result right here. Yeah, so I gotta close you down now. Okay, so yeah, so our events go down to say 30-ish kilometers. Yeah.
So I guess my question maybe still stands about how you have sufficient resolution to see that channel that's sort of fairly deep. Yeah, I have sort of both the vertical resolution, but also sufficiently large anomalies for it to show up. I guess I need to see the paper when it's submitted.
Yes, we are still working on that. There are approximately 1 million panels of resolution tests that I can show you. but I don't have them here. We're still working on that part of it. But I mean, the waves do dive down and they produce that channel. It was like not artificial in any way. So we've done the testing. I just like, you know, I didn't bring the resolution test for every single model, but yes, it's a good question. And yes, we are still working on showing that, but Petros is kind of, I would consider him the master of resolution. I think he'd rather do resolution than like anything else. So it's resolved.
Okay, so are there other questions from the audience? No? Okay, so I have a question. So in terms of the melts present in this lithosphere-asthenosphere, I'm wondering if you have an estimate of the volume of the melt, and like will they be large volume enough that can alter the heat flux through the crust, or large enough that can change the topography, like the bathymetry deviate from this like square root T relationship?
Right. Yeah, that's a good question. So if you look at the kind of the petrophysical inversion there, like, yeah, we had up to 4% melt in these figures here. And you know, if you look here at you can see there's a little bit of weird topography above this largest anomaly. So that's interesting to us. Overall, we don't see huge gravity signature because we think there's a lot of crustal thickness variation in our region, and that's probably because the Atlantic is, you know, variable in terms of the magma supply, and so it's creating thick crust in some cases and thin crust in other cases, and so that usually that surface signature usually dominates the signature of the gravity. And the other thing is that because it's such a slow spreading center, the plate is thick and cold in comparison to the Pacific. And so it's probably stronger, and therefore, you know, we're getting this little jitter here, but we're definitely not seeing, you know, enormous amounts of you know, effects and bathymetry because of the thick and relatively rigid plate. And the other reason we probably don't see gravity anomalies is because if you think about it, you know, you have this downwelling here, you have this upwelling here, they compensate each other on this kind of broader scale. The other evidence, by the way, thinking of this now, and going back to Zach's question, for this lithospheric drip, is that we had a really cool interplate earthquake there. And we are working on doing the moment tensor, because it looks weird already to us, and so we're currently working on looking at the moment tensor to see if it looks like anything related to a drip. Yeah, and that's the only place that we saw like a very strange like earthquake off the you know, off the plate boundary.
Are there other questions? If now we're up to one. Oh, there's the one from Steve Goldstein. Do you want to? Oh, he doesn't have a mic. So his question is, how much melt do you see below and away from the hotspots, spreading centers? Is it model dependent?
Is it what?
Model dependent.
Oh, well, so the melt fraction that we see here, you can see it here. It's mostly below 4%. You know, this is based on these petrophysical predictions. And the melt percentage comes from both the seismic velocity model and also the conductivity model. Yeah, I mean, like if you take, I guess if you take seismic velocity alone, you can often think of like the different, you know, forms that it could come in, and obviously there's this range of melt fractions, but this is kind of the joint investigation of the two. We came to a simple conclusion using kind of simple assumptions. The paper is here, and if you want to give me different assumptions, I'm happy to discuss. But having the two together was helpful in terms of, you know, determining material properties.
Okay. Thanks, Kate. Thanks, Kate, for the presentation that covers so many aspects of the atmosphere lithosphere boundary. And so our next speaker will be Garrett Elo from University of Hawaii, and his webinar will be on February 5th. So the first Wednesday in February, same time, between 3 and 4 p.m. Eastern time. And we hope to see you again next month. And thanks everyone for joining our seminar today.
Thank you.
Okay.